So, now in this new lecture, which is in which we will discuss crystal systems and Bravais lattices, following what we have discussed in previous lectures on which was a background basically on how do you construct a lattice, what do you mean by a lattice, and what is the meaning of a crystal lattice. So far we have talked in generality. So what we have seen is you have a point lattice. In this point lattice you can make a unit cell. Unit cell has lattice parameters. You can make a crystal lattice by replacing points with atoms or group of atoms, and then we talked about primitive and unit cell. But the question still remains in the unit cell is what kind of unit cell you choose. Can you choose any arbitrary unit cell, because there are multiple possibilities are there. You can see that in this, for example, simple example. Let me remove the other ones which are a little far. You can choose this as a unit cell. You can choose this as a unit cell. So there are multiple possibilities. The question is what? Which one do you choose, or is there a basis for choosing a unit cell, and what is that basis? So that is what we will discuss in the next few lectures. In this lecture I will just tell you the established mechanisms to identify these different patterns, and then we will get into why these patterns, what is the basis of making these patterns. So what we basically have here is, we call them, so depending on, so you cannot choose any arbitrary shape first of all, okay. The shapes are divided into few categories, and those categories basically define what we call as crystal systems, okay. So there are a total of 7 crystal systems. Starting from the first one, we call it as a cubic crystal system. So in a cubic crystal system, essentially what happens is you have so you can see that it's nothing but a cube. So now we are talking basically in 3D, okay. So we can say these are the crystal systems in 3D. So you can also have, you can also ask me a question that what about crystal systems in 2D. So I will give you some hints at the end of it, and I'll hope that you will be able to tell me how many maximum possibilities of crystal systems can exist in 2D, okay. So let me first give you the examples of 3D, the possibilities of, and then we will discuss the origins behind these possibilities. So in the cubic crystal system, what you have here is basically the lattice is based on the cubic arrangement of points in space. So every point will follow this kind of cubic arrangement such that, so you have A, B and C. A is equal to B is equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degrees. So this angle and this angle, all the 3 angles are 90 degrees. So between A and B you will have gamma, between A and C you will have beta, and between A and C you will between B and C you will have alpha. So all these 3 angles will be equal to 90 degree. So if your arrangement of points allows you to construct a unit cell, you will go with the cubic unit cell, because as we will come to perhaps in next lecture or lecture after that, this is the most symmetric. What do we mean by symmetry? We will see that in the next few lectures. So we will choose a cubic structure when it is present and when the symmetry permits it. Second choice of this is slight distortion of cubic, which is called as tetragonal. So, what happens here is your unit cell is slightly distorted. So, basically what you do is that you extend this C or compress this C a little bit as compared to the cubic case. So, what happens here is slight, you can say it is a slight distortion of a cube. So, what you will have here is you will still have A is equal to B, but C is unequal, okay, but alpha, beta, gamma still remain 90 degree. So, it's still an orthogonal system. Cube is an orthogonal system, tetragonal is an orthogonal system. So, that is the only distinction that you have. So, the next one is a little bit even worse than that. Third one is called as so, basically you have a tetragonal unit cell and you now change the dimensions along A, B and C, all the three directions without changing the angles. So, what you have here is A is equal to A is not equal to B is not equal to C, alpha is equal to beta is equal to gamma is equal to 90 degree. So, it's still orthogonal, but lengths are not at all equal. So, this is the third variation that you see in this structure. Fourth one that we talk about is called as hexagonal. In this hexagonal system, what you have is basically it looks like a hexagon. So, what you have here is, so you can say that you have a unit cell like this. Okay. This angle here is 120 degree and these other two angles are, so this angle and this angle, they are 90 degrees. Okay. So, you can say this is your A, this is B and this would be C. This is A, this is B and this is C. Let me just, all right. Okay. So, here now the angle between A and B, that is gamma. So, here gamma is equal to 120 degree. What about alpha and beta? Alpha is equal to beta is equal to 90 degree. What is the relation between A and B? A is equal to B, but it is not equal to C. So, why this is called as a hexagonal system? Because when you put three of these unit cells together, they make a hexagon pattern. So, if you make something like that, you will see, let me just try making one for you. So, this will be the first one, okay. This is the second one. Not a very good drawing, but still you can probably see what I am trying to do here. So, this will be the next one, and if I connect it well enough, and then you will have, this is the second one, and then you can draw the third one in front. Okay. So, third one would be something like that. So, these are the three unit cells which are drawn. So, in a hexagonal pattern. So, this face will look like a hexagonal face. So, that is why it is called as a hexagonal system. And now, the next one is called as rhombohedral. In this system, in the rhombohedral system, rhombohedral system can ideally be represented from a hexagonal system. What happens in rhombohedral system is A is equal to B is equal to C, but alpha is equal to beta is equal to gamma, but they are not equal to 90 degree. So, this is what makes a rhombohedral system. So, you can see that it is sort of like a cube, but it is not a cube. You squeeze the cube in such a fashion, so that A, B, C are equal, alpha, beta, gamma are equal, but alpha, beta, gamma are no longer equal to 90 degrees. So, this is called as rhombohedral. There are two more distortions which are there. The first one is called as monoclinic and the second one is called as triclinic. In the monoclinic case, your A is not equal to B is not equal to C, and another difference is that alpha is equal to beta is equal to 90 degree, which is not equal to gamma. So, gamma is an angle which is not equal to 90 degree, but it is not necessarily, as you can see in the hexagonal case, it is necessarily 120 degree. In this case, it does not have to be a necessary angle, it is just not equal to 90 degree, it can be anything else. In the triclinic case, this is the least symmetric of them. You can see A is not equal to B is not equal to C, and alpha is not equal to beta is not equal to gamma. This is the worst of them. So, in terms of symmetry. Okay, so these are the crystal systems that you can see in 3D. So, what you have here is, so this is the cube, second one is tetragonal system, third one is orthorhombic, fourth one is monoclinic, you have triclinic, you have rhombohedral. Rhombohedral is often also called as trigonal or trigonal system. Okay. So, here all the three angles are equal, alpha, 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 but they are not equal to 90 degrees, and A, B, C are all equal, and this is the hexagonal system. So, this is the basic unit cell in the light green. So, you can see the gamma is equal to 90 degree, A are equal, but they are not equal to C. Okay. So, this is the three crystal systems in 3D. So, I'll give you a bit of homework. You can get back to me in the next class, or I will discuss that in the next class, that what are the possible crystal systems. So, you have 7 crystal systems in 3D. How many possible crystal systems? They will not necessarily have different names, same names, okay, because remember there is no third direction, there are only 2 directions. So, they will have different names. Forget about the names, but you just have to think about what different geometries are possible in 3D, and can you generalize them. You see, the point is about generalizing them. Here we have generalized. Okay. Can you generalize a few crystal system, maximum possible crystal systems in 3D. So, once you know about the crystal systems, what we talk about now is called as Bravais lattices. Okay. Bravais lattices are a further up from crystal systems, because they now consider whether it is a primitive lattice or whether it is a non-primitive lattice. Again, the reason for choosing particular type of Bravais lattices will be discussed later on when we talk about symmetry, but let us see just on the basis of primitive and non-primitive unit cell what kind of lattices are possible. So, in case of cubic system, you have 3 primitive lattices which are possible. First one is called as simple cubic lattice that we have seen. So, simple cubic lattice, you can see that how many number of atoms does it have? It has only one, so it is a primitive lattice. That is why there is a letter against it which is called as P. P means primitive. Anything which is not P is not primitive. Okay. So, second possible variant in cubic systems is that you can make a body centered cubic lattice, where you have one lattice point at the corners and the second lattice point is at the center of the unit cell. These two are identical lattice points. So, which means if these were 2 different atoms, this will not be a body centered. What will it become? It will become simple cubic lattice. So, these 2 points have to be identical. If they are identical, then this can be called as a body centered cubic lattice. Third possible variation in cubic system is face centered cubic lattice, where you have points at the center of each of the faces. So, you have 6 faces in a cube, all the 6 faces will have lattice points at the center of these faces, along with corners being occupied. So, total number of lattice points in this system now becomes 4 because you have 8 at the corners which are shared by 8 unit cells. So, 8 divided by 8 is equal to 1, and then you have 6 at the faces, but each face is shared by 2 unit cells. As a result, you have total of 3. So, 3 plus 1 make it 4. So, you have 4 identical lattice points. Again, in this case, if any of them becomes different, it does not remain as a face centered cubic lattice. That is the takeaway, but they follow the same definition of cubic crystal system. Second variation in this case is tetragonal lattice. In case of tetragonal, you can see that so in the tetragonal, again you can see the C is different than A. So, this is single tetragonal. You have 8 points at the corners, and since you share each of the unit cell by 8 neighbors, 8 neighbors share 8 unit cells share 1 lattice point. As a result, this is 8 into 1 by 8. So, 1 lattice point. Again, here you have body centered tetragonal. So, you have 1 lattice point here, under here, both are identical lattice points. So, you have 1 plus 8 into 1 by 8 is equal to 2 lattice points. In the previous case, it was 8 into 1 by 8 plus 6 into 1 by 2. This will make it 4. Okay. Now, let us see the third example. So, you can always ask me a question. Now, you can see that there are other possibilities also. So, you can ask me a question, for example, why do not you have a cubic system in which you do not have at the edges, for example, why do not you have an edge centered cubic lattice? I can ask a question, why do not we have a face centered tetragonal, and we will answer those questions later on. There are crystallographic reasons, symmetry related reasons which do not permit the formation of a body centered tetragonal, a face centered tetragonal lattice. So, in case of tetragonal, there are only 2 possibilities, 2 distinct possibilities, simple tetragonal and body centered tetragonal. This is primitive and this is non primitive. Remember, body centered systems are represented as I. Okay. So, whenever you have in the crystallographic terms any lattice represented as P, which means primitive, I it means body centered, and F means it is face centered. Okay. So, these are crystallographic notations which will be useful for you to remember to identify or distinguish between various lattices. Third one is called within orthorhombic. Now, you have 4 categories. Simple orthorhombic, same as simple cubic and simple tetragonal. So, again it is P. You have body centered orthorhombic, which is same as body centered tetragonal and body centered cubic in terms of its understanding. So, it is I. You have face centered tetragonal orthorhombic, which is built in a similar fashion as you made face centered cubic lattice, but within an orthorhombic framework. The next one you have is base centered orthorhombic. Okay. So, which means what you have here is on 2 of the faces, 2 of the opposing faces, you have an atom or a point sitting at the center of the faces. Okay. So, you have 1 point here, 1 point here. So, total number of lattice points in this case will be 2, because you have 1 by 8 into 8 plus 1 by 2 into 2. Now, this option you can see is not available in tetragonal and in cubic, and why is it not there, that we will discuss later. The next option next possible variation that we have is of rhombohedral crystal system. In this case, you have only one lattice which is called as rhombohedral. Although it is a primitive lattice, we designate it as a R. So, rhombohedral systems, the primitive lattices of rhombohedral systems are designated as R. In case of hexagonal system, you have again only one kind of lattice, that is primitive hexagonal. There are other variations which are not possible. In case of monoclinic lattice, you have simple monoclinic, which is primitive, and you have base centered monoclinic, same as base centered orthorhombic, where you have 2 opposing faces having atoms. So, you have AB face, 2 AB faces have atoms or points at the middle of those faces. Okay. So, this is a base centered question. Again, you can ask a question, you can think about, can you have any 2 opposing faces, or do you need to have a specific 2 opposing faces? Okay. In case of orthorhombic, it is simple to answer. It does not need to be only these two faces. You can have centers of these faces as atoms, but only two, either these two or these two or these two, because it is an orthogonal system. However, monoclinic is not an orthogonal system. So, question that arises is, do only these two faces must have should only these two faces have atoms at the center of these, or you can have at these also or these also, but only two at a time. So, just think about it, and we will answer some of these doubts in the next few lectures. Third and the last one is triclinic, where again only a primitive option is possible. So, you can see that there are various non-primitive lattices which can be built, but only in a few systems, in cubic, in tetragonal, in orthorhombic, and in monoclinic. Rhombohedral, hexagonal, and triclinic do not allow you to have any other possibility. So, how many of Bravais lattices do you have now? So, you have 14 Bravais lattices, 7 crystal systems and 14 Bravais lattices. The number of combinations go down in 2D. In 2D there are different numbers, and I will just allow you some time to think about it before I give you the answer in the next class. So, a number of possible. So, this is the sort of a summary slide. You can see that there are 7 crystal systems. In case of cubic, you have PIF. P means simple or primitive. I can write this, simple or primitive. Okay. So, P means primitive or simple, I means body centered, F means face centered, C means end centered or side centered or base centered. So, any of these is called as C centered. Okay. So, you can see cubic has P, I, F options, but there is no C option. Tetragonal has P option and I option, but there is no F option and C option. Orthorhombic is the most versatile. It allows you to have primitive lattice, it allows you to have body centered lattice, it allows you to have face centered lattice, and it allows you to have C centered lattice. Again, hexagonal is only primitive, trigonal is only primitive, monoclinic is primitive and C centered, triclinic is only primitive. So, now the question that arises is, why don't you have this? Why don't you have this? Why don't you have this? Let us first discuss these few cases, and once you understand these cases, everything else will become clear about other cases as well. I mean, the only thing that you have to worry about then is probably the monoclinic C case. This is not possible, but you can see why this is not possible, because monoclinic is very less symmetry lattice. As a result, it is not possible to make a non-primitive structure, because remember, lattice has to be periodic. So, that periodicity of lattice translation symmetry and other symmetry, as we will see later on, should be obeyed. Okay. So, effective number of lattice points now you can calculate. So, for a primitive systems you have only 8 corners, so number of lattice points is 1. For body centered system you have 8 corners and 1 body center, so total number of lattice points is 2. So, this is 8 into 1 by 8 plus 1 into 1, this is 8 into 1 by 8. In this case it is 8 into 1 by 8, and this is 6 into 1 by 2, yeah, sorry. And again here you have 8 into 1 by 8 plus 2 into 1 by 2. This gives you the total number of effective atoms in the unit cell. So, the questions that we now want to answer is, why do we not have 28? Because there are, as we saw in case of orthorhombic, there are 4 possibilities. So, why don't we have 28 Bravais lattices? Why do we have only 14 Bravais lattices? So, why are some of them missing, and what is the basis of classification? And the answers will be given in the symmetry. So, these answers will lie in symmetry considerations. Symmetry considerations are typically not talked in any of the standard elementary textbooks of material science. So, this you may not find in the references that I have mentioned in the beginning of the lecture series. So, this is something that you may feel a little bit more attentive to, or I will give you some references which are different references to read them about. So, to summarize, let me just go to the last slide. You have a points lattice which is ordered array of points with identical neighborhood. You have a unit cell which is within a point lattice, which can be smallest repeatable unit whose size and shape can be characterized by defining lattice parameters. A crystal lattice can be defined as point lattice with motif or basis, this which is an atom or group of atoms. A motif or a lattice point, so we normally call it as a lattice point. A motif or a lattice point can be either an atom or a molecule or a group of atom or a group of molecules. Okay. And depending upon the relative positioning of these atoms and molecules with respect to each other, you define lattice into two different types. One is the primitive lattice, second is the non-primitive. The definition of primitive lattice is one lattice point per unit cell. We call it lattice point, not atom, because atom is little misleading. The moment you have more than one atom, depending upon their relative distribution with respect to each other, the definition changes. So, you may have one atom, you may have two atoms, you may have three atoms, you may have several molecules within one lattice point. So, that is why we refer it as a one lattice point. Okay. So, this is one lattice point per unit cell makes a primitive lattice, and this can be very big unit cell within a lattice depending upon the relative orientation. And then you can have non-primitive one, which has more than one lattice points per unit cell. And then we saw, since there are multiple possibilities of unit cell, you just said earlier, we just said that it is a smallest repeatable unit. We did not talk about the shape and size. Okay. So, the question arises is, what are the possibilities? Can you have infinite number of possibilities? So, instead of having trouble of finding in this infinite possibilities, let us define certain criteria, and that criteria, as we will see, is based on symmetry. It is not an arbitrary criteria. So, based on the considerations that we will see later on, there are 7 crystal systems, and based on those 7 crystal systems, considering primitive and non-primitive considerations and symmetry considerations, there are 14 Bravais lattices. So, this is the basic introduction to crystallography. In the next few lectures, we will look at what is the underlying reason behind 7 crystal systems and 14 Bravais lattices, and that is where you will also understand the importance of motif or lattice point. That will become more clearer as you correlate this to symmetry. Okay. So, we will wind up here. Thank you very much.